Hey Mustangs, in this video we're going to be taking a look at some more practice problems for chi-square. So in this one we have our first word problem here. So in pea plants, yellow seeds are dominant over green seeds. So we know what's dominant, what's recessive. Cross two plants that are both heterozygous for seed color. So if they're heterozygous, we're going to use, let's say, capital S equals yellow and little s equals green. If we cross two heterozygotes, big S, little s, with big S, little s, we did a Punnett square, we'd find big S, big S, big S, little s, big S, little s, and little s, little s. So basically what we have here, these would all be yellow, and this would be green, so we have a 3-to-1 ratio. That would be our expected outcome if this is complete dominance. Now, we could also do it in percents. We'd say like 75% to a 25% ratio is what we're looking at here. Okay? So, based on this outcome, we're going to say that our null hypothesis is that there will be no difference from the expected 3-to-1 ratio for complete dominance. Okay, so there would be no difference. We expect it to be this. So we have to calculate what we should expect from this. So in order to do this, we have to look at what we actually observed. So there was 4,400 yellow and 1,624 green. So if we add that together, we get 6,024. Okay, so that's the total amount of offspring that were born. And we want to see, okay, if there is a 3-to-1 ratio, 75% yellow, 25% green, then we have to take this total and multiply it by those numbers. So then we would say for the yellow, we'd go 6,024 times 0.75, and that will get us our expected values for yellow. And then for green, we go 6,024 times 0.25, and you should get for the yellow 4,518. For the green, you should wind up with 1,506. So these are our expected values if we're following this 3-to-1 ratio. All right. Now we have to perform a chi-square and see if these numbers are acceptable. When we look, we see 4,518. Is that close enough? Is there something else going on? Here, 1,624, we got 1,506. So are those close enough to the 3-to-1 ratio? Or is there some other mode of inheritance? Or is there gene linkage going on here? So for the chi-square test, chi squared equals the sum of all the observed minus expected squared divided by expected. Mouthful. So you go observed minus expected. So we'll start with the yellow. So observed is 4,400 minus the expected of 4,518. And then we square that value. Then we divide it by what we expect as well. So 4,518. And it's the sum of, so we also have to do it for green. So our observed for green is 1,624 minus our expected 1,506. Square that. Divide it by the expected 1,506. Okay. So if you solve this, you should get 3.08 for this right here. And over here, if you solve this, you should get 9.24. Right? If we add these two together, so we add those two together, you wind up with 12.33. Now what does that mean? We'll see in just a moment. So degrees of freedom. To calculate degrees of freedom, you take the number of things you're comparing. So we're comparing two things, yellow and green. So 2 minus 1, and that equals 1. So 1 degree of freedom. So we look at our degrees of freedom chart, and this is what they would give you for the AP exam. So we have 1 degree of freedom. So degrees of freedom are listed on the top here. So here's 1 degree of freedom. Here's the critical value. So the probability of 5%, which is represented by 0.05, if it's 3.84, that's the critical value. If it's 3.84 or a bigger number than 3.84, that means you have to reject your null hypothesis. If it's 3.84 and it's a smaller number than 3.84, then you would say your hypothesis is supported. So here's our critical value number, or here's our critical value number. We compare this to that. That's definitely bigger. So we see that it's bigger than 3.84. So we're going to say we reject our hypothesis because the number is greater than the critical value. Okay, so that's our critical value right there, and it's greater than that. Okay, it's definitely a bigger number than 3.84. All right, next example. This is a big one. So this is if you did a dihybrid cross. Okay, so if we look here, we see white flowers are dominant to red, and short plants are dominant over tall. So we're comparing 2 different traits here. 2 tall, that we're using heterozygous again. So 2 tall plants that are heterozygous for both traits are cross, resulting in the observed phenotypes. Now, here's the trick. You don't have to do a full dihybrid Punnett square for this one. So when we say heterozygous right here, we know that if you're doing a dihybrid cross with 2 heterozygotes, you should expect a 9:3:3:1 ratio. Okay, so these should fall into the category, a 9:3:3:1 ratio. So our hypothesis will be there will be no difference from the 9:3:3:1 ratio based on complete dominance. Now there could be other types of dominance here. There could be epistasis going on. There could be linked genes. So we need to find that out. So in order to do that, we do a chi-square test. So expected, in order to calculate the expected, we add up the total. So 206 plus 83 plus 65 plus 30, and you should wind up with 384. Okay. Now, these ratios, if we add this all up, 9 plus 3 plus 3 plus 1, there's 16 total. Okay? So if we want to find the percents to multiply by, we go 9 divided by 16, and that would give us a percent, 3 divided by 16, and so on and so on. Or we could just do it like this. So for white, short, it's 384 times 9/16, because 9 divided by 16 would give us a percent value, and then that would equal. And then we would do white, tall, and it's 384 times 3 divided by 16 equals. And then we have red, short, is 384 times 3/16 equals. And finally red, tall, 384 times 1/16. Okay, and that's the most recessive. So red and tall, so we don't expect 1 out of 16 to be red and tall. So when we calculate these out, you should get 215, 73, 73, and 23. Okay, so if you do the math on those, I'm going to do a little divided line there. Okay, so these are our expected values. This is what we would expect to get if it is following the complete dominance hereditary patterns. So then we do a chi-square. So chi-square equals the sum of, so we have 206, which is what we got for the white short. So 206, the observed, minus the expected of 215 squared divided by 215, plus we have next the 65 white tall, right? So 65 minus 73 squared divided by 73, plus, then we do red short. So red short, we have 83 minus 73 squared divided by 73. And finally, we do the last one, 30 minus 23 squared divided by 23. And if we do these numbers, you should get 0.38 here, 0.87 here, 1.37, and 2.13. And if we add all of these together, you get a value of 4.75. Now you might be thinking of the last value of 3.84 being the critical number, but in this case it's not, because we have different degrees of freedom here. So we look here and we have 1, 2, 3, 4. We're comparing 4 things. So to calculate the degrees of freedom, we go 4 minus 1 equals 3. So we're looking at 3 degrees of freedom here. Okay, so if we look at our chart here, it's all covered. So our value is 4.75. So I'm going to erase this so that way we can see the chart better. So 4.75 is the number we got. All right, so we got the number of 4.75, and then we calculated our degrees of freedom. 4 minus 1 equals 3. So here's our 3 degrees of freedom, and the critical value is 7.82. That number, or a bigger number than that, would mean we'd have to reject our hypothesis, and that maybe the genes are linked or some other mode of inheritance like codominance or incomplete dominance is going on here. So we have 4.75, which means our null hypothesis is accepted. The values we got are close enough to that 9 to 3 to 3 to 1 ratio. So our hypothesis is supported. The number was smaller than the critical value of 7.82.